Okay, in this I'm going to introduce the concept of concavity. So we are going to define those sketches and then do some examples involving test of concavity. So definition. So let f be a differentiable function on an open interval AB. Then one, f is concave up on AB if f prime is increasing on AB and then 2, f is concave down on this open interval AB if f prime is decreasing on AB. So we are going to draw sketches to represent these two aspects. So in the first figure, we are going to draw the sketches for concave up. So concave up. So this all these are shapes of concave up. So this A, B, and C. And concave down so we have these shapes. So this A, B, and this C. So these three figures shows the shape for concave down. And then if we have a graph or a curve for concave up, let's have these two sketches, one for concave up and another one for concave down. So for these two graphs, if you draw tangents to these two graphs, so we have this. Then we have this. Then we have this. Then on this other one we have this. We have this. And then we have this. So so this f prime is less than 0, f prime is 0, and then f prime is greater than 0. For this other case, f prime is greater than 0, f prime is equals to 0, f prime is less than 0. So as we move from left, so this is for concave up. So slope of tangent lines are increasing. So remember, we are starting moving from left. So this negative 0, then positive. And then for this concave down, slopes of the tangent line are decreasing. So as we move from left, this is positive, then 0, then negative. So that's what we have. So test for concavity. So theorem. So assume that second derivative of the function exists for all x in this open interval AB. So then 1, if the second derivative is positive, that's greater than 0, for all x in this open interval AB, then f is concave up on this open interval AB. And then number 2, if the second derivative of x is strictly less than 0, which that means negative, for all x in this open interval AB, then f is concave down on AB. So that's what we have. So this is the test for concavity. And then the second theorem. So test for inflection points. So this theorem that you are going to state will help us to know the inflection points for a curve. So if the second derivative of x equals to 0, or so second derivative of c, or second derivative of c does not exist, and f double prime changes sign at x equals to c, then F has a point of inflection at x equals to c. So that's what we have. Another thing that we need to know, so next session we'll be giving examples. So for points of inflection, we have these sketches. So we have this. Actually, this just other graphs were showing. So this point P so this is concave down. This other one shows concave up. While this point P here, P is the point of inflection. P is a point of inflection. So just a formal definition of points of inflection. Say, let f be a function that is continuous on an open interval, and let's say be a point in the interval. If the graph of f has tangent line at this point, say comma f of c, then this point is a point of inflection of the graph of f if the concavity of f changes from upward to downward, or downward to upward at the point. So that's what we call a point of inflection. So the second derivative test, so theorem, the second derivative test. So it says that let f be a function such that f prime at c equals to 0, and the second derivative of f exists on an open interval containing c. So 1, if second derivative at c is strictly greater than 0, then f has a relative minimum at c comma f of c, and 2, if second derivative at c is less than 0, then f has a relative maximum at this point c. Now, if second derivative at c equals to 0, the test fails. So that is, f may have a relative maximum, a relative minimum, or neither. So in such cases, we use the first derivative test. Good. In the next session, we'll be doing examples on concavity and second derivative test. Have a good day.